Good morning from my side. I'm from Master Pillars, this is correct, but I also worked as assistant professor at the Mining University and as a site manager and designer, just to position myself when I touch design considerations. Reducing carbon footprint. This is very close to my heart, and you may ask yourself, why do we talk about this? Yeah? I think we cannot ignore the global warming. This is visible everywhere, whether it's the nice evenings, nice warm evenings, maybe the shortage of water, the heavy rainfalls, and all the rest that goes with it. So what's our role in that, and what is driving it? And I think it's common or accepted ground that the carbon dioxide, which you see up here on the bottom, the light blue is the key driver to the global warming, the man-made key driver. So what's our role in that? Why do we, as construction industry, care about that? Cement is contributing 8% to the global warming. I know this is very much towards China, but in global it's about 8%. And then I know that, or you may have heard that there's lots of complaints about the aviation industry. Aviation stands for 2 to 3%. Germany as a country for 2%. We talk about 8% for the construction industry. So why should we as tunnelers care about it? We use cement, but that's it. We work with the ground. When you do analysis of a tunnel in terms of CO2, and we did this, and the basis was a PhD work from a German lady, 2016, Brenner Base Tunnel. Up front, 230 kilometers in total, a mixture of TBM and drill and blast, NATM, or whatever you want to name it. And the outcome is, of the total, underline total, construction CO2, 66% come from the cement only. And in the cement it's the clinker. 18% has to do with the rest of the concrete. Means a bit the aggregates, the chemistry, the reinforcement. And only 16%, is very little, is to manufacture the TBM, to drive at the job site, and the rest is very little. What should we learn from that? If we really take it serious and want to reduce the carbon footprint at the tunneling job site, we have to focus on what? Gas. We have to minimize the concrete volumes. You can ask yourself, how much concrete do we really need? Where are the hidden safety factors? And the concrete we use, we have to optimize. We have to minimize the clinker in the mixes. That's the two key messages. Of course, we can use electric cars, nothing against that. We can reduce a material from 2 millimeters being thick to 1 millimeter, adds a bit, but don't expect a big change. The big change has to do with the concrete. Concrete volumes, and in the concrete, the mix design. So how can this be achieved now? That refers to the title, Review the Tunnel Design for the Total Concrete Volumes. I've touched a composite and written underneath in brackets something I will work out a bit now. How much is your inner lining really loaded? What I say now is a bit exaggerated, I know this, yeah? But we do a tunnel, let's say in drill and blast. We spray, we support it with sprayed concrete, we keep on driving it, we monitor the deformation as you have seen in the millimeter, centimeter range. We don't talk about meter deformation or 1.5 as in the Karawanken tunnel. In the centimeter range, it levels off. Then we come typically with a sheet membrane, and then we place the inner lining. So now let's guess, ignore the water for the time being, and ignore creep a bit. So what is loading the inner lining? The only load that goes on the inner lining apart from the water pressure is the deformation. What else should load it? So is there any deformation? And if the answer is, maybe not. So what is the inner lining then loaded? Why do we build a 1 meter, half meter, 400 millimeter thick inner lining if it's not loaded? Okay, we can talk about the the water pressure on this. But let's pull this apart. This is the starting point we really have to think of. What is the load of the inner lining? So now let's go to composites. Composites is when two linings are somehow glued together. You have a primary lining, that's typically the support you spray when you advance. Then in our case, you have a spray applied membrane that bonds to it, really bonds. It is not mechanically fixed, as you can do with sheets, it's bonded. And then you cover it with concrete, whether it's sprayed or cast. And then you have a composite. And the composite acts as a composite. In terms of load shearing, to which extent you can debate how much load is transferred via the membrane in between. Is it really needed? Question mark. You talk about the load of the inner lining, all this. But in principle, the outcome is you can reduce the lining thickness. You can really reduce it. Think of something when you do a tunnel of a 10, 30 meter span, which is quite usual, and you build an inner lining of, actually you could do your calculation and you land on 10 centimeter inner lining needed to build it. But you cannot build a cast concrete arch with 10 centimeters in a span of 30 meters. It's impossible. That means you somehow have to glue it the first lining, which is then a composite again. Whether you do it in a calculation considered or not, it is a composite. That we talk also about the buildability of a composite. That means the first step is think of your load of the inner lining and then how you build it best. Composite is a smart option. I will touch this again. And then in the mix design, in the concrete, you really use what can you do to optimize it. And the key is take clinker out. I know for sprayed concrete, this is very close to my heart. It has to stick to the wall and gain strength. We need the safety and everything. We need the support, yes. Is anyone from the cement industry around? We need good reactive clinkers. Good reactive clinkers in a reliable quality that we can work our mix designs without big safety margins. Reduce the clinker, use SCM supplementary cementitious materials like the fly ash and the slag and the limestone powders and anything else, or calcined clay to come later down the road. Use them to reduce the overall carbon footprint. And then one thing to the designers and owners, now it's a wish. It's a wish, yeah. There's the word optioneering. If you take it serious, then you have to start from day one, when you think of a project, to take the CO2 reduction serious. It means global warming must be part of the design criterion, not only cost and time frame. Also global warming. So now you have to run a calculation on the global warming and you don't know actually the details of the alignment of the tunnel, or you have maybe 5 options and one is a TBM or 2 are TBMs, 3 are others, and then it can be a double or a single tunnel, lots of options. So what can you do? You have very little information. Then the next wish is be pragmatic. Take generic data. For a linear meter, you need that much concrete of certain, let's say, global warming potential, and do a mathematics, simple mathematics. And this is the first thing you can do. Takes not much time and gives you a clear guidance. And if the results are about the same, who cares? But if they're a big difference, then give it a second thought and sharpen your pencil a bit and review it again. And then, if this is not somehow part of a contract, CO2 reduction, nothing is to happen. I'm not naive, I'm too long in the industry. This all must be part of a signed contract. There must be a goal for anyone, whether it's the designer looking from the owner, down to the designer, to the construction company. If there is no incentive in, nothing is going to happen. I copy-paste what I've always done. I've spoken to many of you, and what I also did, copy-paste is the quickest way and reduces my risk. So if you want something different, then let's act differently. And get it signed. Let's look into numbers a bit. This is a cubic meter, or actually 2 cubic meters of concrete for our double shell lining now. On the left-hand side is sprayed concrete. The gray part is the concrete. No, sorry, the cement, the binder, you could say, in the mix design. We land on, in this case, 450 kilogram CO2 per, or equivalent per cubic meter, which is quite high. Below 400 would be fantastic. 400, 450, maybe that's the average. The gray stuff is the binder. The browny stuff is the rest in the mix design. And the black one is the reinforcement. On the right-hand side is a cast inner lining which comes in lower, is less cement, less reactive cement typically, and since this is Austrian example, is unreinforced. Just to put some additional numbers to it, you could ask, what about the transportation? I've written A1 to A3, which is more or less produced at the factory. You could say cradle to gate. It's not delivered and placed. We talk about the spread concrete here, 400, what about the concrete? Let's say 400 kilos CO2. To mix a concrete, a cubic meter of concrete, to transport it to the job site, let's say 30 kilometers, and to spray it is in total 10 to 15 kilos CO2 in addition. It means if you don't know the numbers in the early assessment, you can ignore them because it's the same anyway for all the options. And it doesn't completely change the picture unless you transport it over hundreds of kilometers. Then it's a different story. So if you want to do mathematics now on your tunnel, you need a cross section. No, sorry. First, we need to optimize this. And if I do a material optimization, it has to do with binder optimization. This is clear. I take out clinker bit, try to replace it with more reactive clinker, and overall I get a bit down on an optimized mix design, which is, by the way, again being used at Austrian job sites. Nothing from the drawing board. It's used in Austria. This is standard practice. I get the 450 down to the 360 in this case, yeah? And the inner lining is a bit less to gain, but that's the numbers. And I want to know how many kilo or tons CO2 I need per linear meter of tunnel, then I need the geometry. And to make my mathematics easier, I used a round shape. I know this is not right shape for an NRTM tunnel, maybe for a TBM, yes, but forgive me for that. It is 250 millimeter sprayed concrete with 2 layers of mesh, 1.3 meter advance lengths with lattice girders, and the 400 millimeter cast inner lining, and the sheet membrane and geotextile in between. Then we do the mathematics for our 10 meter diameter tunnel, and that's the outcome. The NRTM standard is the left-hand side, the sprayed concrete, not improved mixed designs. You land on nearly 12 tons for the structural support, 12 tons CO2 for the structural support for linear meter, out of which is the blue part, the sprayed concrete first layer, and the brownish part is the cast concrete. So I have to add some more statements to that, to the numbers. If you do the mathematics yourself, you will get lower numbers. Why? I think everybody in the room knows that we use more sprayed concrete than as per design is being asked for. The factor, when I started, was 3. We were in the dry days, now it's about 2. I have added, based on my discussions with my ex-colleagues from site, to the design thickness of sprayed concrete 150 millimeter for excessive thickness, the overbreaks, the unforeseeable overbreaks or whatsoever, or to meet the minimum thickness, and 10% for the rebound and the rest with the overconsumption, rest volumes and discharge and whatever, and 10 centimeter for the cast inner lining. So now we do the optimization of the materials. You get it down by 2 tons to below 10. So what has to do with design now? Now the big step comes, and I call it aggressive design. You cannot do it everywhere. You cannot. But give it a thought. It's just to get you moving. The right-hand side is a composite design, means the layers act in concert. As a rule of thumb, you may chip off 25–30% of the total concrete thickness if this acts. You can ask yourself, how much do you really load? How much load is really transferred onto the inner lining in the long run? Creep and so on, yeah, for the bread. And then it's optimized. And then, in addition, you can ask yourself, if we all know that we overspray the concrete always, that we ask for 25 megapascal, job site measurements show 50, 60 megapascal. Why can't we specify higher? Why can't we incorporate the overspraying to a certain extent? Can't we reconsider the minimum thickness? Why is the minimum thickness everywhere the minimum thickness? Why not treat it differently? Then all of a sudden you get down, and it's parts of this is incorporated in the aggressive design, not all. It means maybe this is out of reach for many projects, but it's possible in some projects to get it down to half, which is a number. Maybe you land on 20, 15, 20, 30%, but even more is possible. What you have to do, be open and come early with your ideas to the party, not too late. Otherwise, the train has left the station. So, composite lining, when can it be efficiently used? And the starting point is a double bonded, not double fixed, it's a double bonded spray applied membrane. It's very much for complex geometry. Think of something you want to waterproof a lining and it's very complex with rather inflexible sheets. It's tricky, spraying is easy. That's obvious. If the inner lining that you need is not so thick, if the mathematics tells you need 150 millimeter and the people tell you below 400 I can't build it, then consider it. Hard rock, that's obvious. In hard rock you can follow with your structural, I need 3 more minutes, thanks for the reminder. In hard rock you can follow the contour with your 50, 100 millimeter. You leave an undulated stuff. If you want a waterproofing, follow the contour with a spray applied, easy, and then cover it again. That's obvious. Innovative designs, that's here, sprayed, final lining, and cast sidewalls for the reflection and cleaning. Super. And to be very fair, if it's really wet in your tunnel, don't consider it. You can treat the water, but if it's too much water, it's useless. It works, but it's not worth the effort. Refurbishment, bottom right example, brilliant. And when you can manage the water pressure. But give it a second thought on water pressure soft ground, water pressure hard rock is different game. Yeah, you have theoretical high water pressure and really low one. Sorry now to come to the example just not far away from here, it was mentioned. The Bekel emergency exit tunnel, originally designed with cast concrete, 300 millimeter, changed on short notice, thanks to the owner and the designer, to spray applied membrane and spray applied inner lining. You see the application they already applied, spray applied waterproofing at the bottom. And this is how the tunnel looks at the very end. It's rough, you have to live with it. But it did the job. I've heard that Andre is somewhere here, that even after heavy rainfall it was very dry inside. It did the job, obviously. And we have to do the mathematics on it, to be fair, because I started with that. That's the mixed designs, 2 spray applied linings. The lower one, for the permanent one, comes in with less heat, less cement, less reactive clinker to minimize the thermal shrinkage. Cast inner lining was not used. And if you do the mathematics on that now, I said the spray concrete first lining was left with 150 millimeter. The inner lining was changed from the 300 cast to 120 spray applied. And the total reduction in this very short, small tunnel was 75, 80 tons CO2. Could say it's not so much, but at least a good start, and a good reference, and a good training. That's what I recommend to everybody. Give it a chance, try this, it works. If you do it right, it works. And you need to invest in good people and good labor, unfortunately. Yeah? If you drive it to the limit, we need better people at job site. And that's why, this was one too much. That's why on my last slide is already written, tunneling is a team effort. It's really a team effort. It starts with an open owner, with a designer that is somehow key to all this, an applicator that does it, and that also invests into the skill set of his people, and to all of us in the room to work on the standards. If we update our standards every 10 years, don't expect that you find the new ideas at the job site. We have to be faster. Back to the team effort. Let's do it. The environment and us and everybody that follows us has deserved it. Thanks a lot.
Thank you, Aldrian, for this really interesting thoughts. I share opinion with you that we use concrete like water sometimes, just spraying and concreting everything. So this is really also my concern. I think we could, in not only tunneling but also in other constructions, we could use really less concrete. So are some thoughts or questions from the public? Yes. Just a second. You'll get the microphone.
Tina Marolt, Liverpool John Moores University. I understood that you would like to reduce and optimize the use of concrete, but what is your opinion on using cement-free concrete in tunneling engineering?
We do as a company look into that for quite a while. It works. It is, when you look at the details, is often quite difficult to use it because of dangerous ingredients, health and safety requirement. It has been done as job sites. I don't believe that in the near future this is taking a big portion of it. There will be some locations like shafts maybe or the other, or definitely when you have aggressive water, aggressive environment, then it may make sense. That's why we use it for some special pipes, for example, fabricated pipes on geopolymer concrete. This works. But in my opinion, the next 10 years, we have to live with what we have, means make it better. It's not a revolution, it's an evolution. But this is possible, we can do it today. We can start, let's be open, do it. We have all the ingredients we need. What we only need to do, and this refers a bit to Arnold, it's the lawyers that sometimes stop us, or the risks that no one wants to share. This is not a technical approach, this is what stops us is more the being risk adverse. No standard, I can't do it, yeah, or whatsoever, yeah. But if the owner ever says, let's try it in an emergency tunnel, why not there? And listen to suppliers, they are quite open, they're very often at the front line. Invite some, have a discussion, bring them to the party, very early in design phase. They might have good ideas. And know where the limits are. What I talked about doesn't work everywhere, but it works very often.
Some more questions? Thank you. It seems that it's more a philosophical question than a technical. Thank you very much, Aldrian.